Okay, I guess everybody's back, so we can start. Again, questions, more questions, something that came to mind while you were having coffee. Okay, so I'd like to kind of wrap up this argument, trying to understand better what's going on here, which is why I've never erased those Feynman diagrams and the equation up there on top. So in particular, what I'd like to understand is whether, so you see, let me remind you what we just did. So we started with this factorized expression. Then I determined the q-square dependence of Cn, starting from the fact that actually An was scale dependent. And then I kind of reshuffled the scale dependence in such a way that at the end of the day, you see, compare this equation with the next equation. It's as if the q-square dependence as leading order has moved from this guy to this guy, right? Because you see, here now the q-square dependence has all gone inside the PDF, so the matrix element. So you can think, but is this just a mathematical trick where I just reshuffled things from one side to the other, or does it have a deeper meaning? It does have a deeper meaning, and this deeper meaning is at the origin of QCD factorization. And in order to understand this, we have to go back to this redefinition with renormalized and bare. And in particular, I want to make the following, actually, sorry, maybe it's easier if I do it here. I want to make the following observation. You see, in the argument that we just went through, I was arguing that when I renormalized, I introduced a scale dependence of An, but this scale dependence must be absent in F2, and therefore the scale dependence must compensate between Cn and An. But hang on a second. There is another thing which must compensate between An and Cn, which is the divergence. Because look, I mean, this guy here is a moment of the structure function, and this is something that I measure, right? So it's some number which I get in an experiment, okay? And this, then, if I look at this sort of expression, I can think of as something where I have some An bare, and this is divergent, and this is what I get when I compute the Feynman diagrams before renormalizing anything, which means there must be correspondingly a Cn bare, which is also divergent, in such a way that when I actually rewrite this as An renormalized, and remember, An renormalized was An bare divided by Zn. Here there must be some C renormalized N. So I guess what I'm saying is that, you know, in my previous lecture, I kind of cheated because I said I start with some expression like this. Then I told you how to renormalize the ANs, and then I started arguing about what happens to the CNs. But surely, if I divided these ANs by some coupling, I must have been doing also something to the CNs, because if the CNs had remained the same, then, you know, I would start with something divergent, and then what am I doing to the divergence? So I kept quiet about this, but I was tacitly also renormalizing the CNs. So I must say that, well, just like I had a bare Cn, which then became a renormalized Cn by dividing out, by dividing out An bare evaluated at scale mu square, which was like An bare times some coupling Z times some renormalization constant Zn. Well, there must be some Cn bare here where I actually multiplied by the same constant, An bare mu square. And likewise here, I have that this is Cn bare divided by Zn. So you see what I'm saying. I'm saying that when I went from bare to renormalized, I actually multiplied the bare thing by some renormalization constant, which corresponds to dividing out the value of the thing at the scale mu square. But correspondingly, I must have also changed my C bare by going from some divergent bare object to something where I actually divided by the same constant by which I have multiplied. So when renormalizing AN, because the whole thing must be finite, because I measure it, I must have been shuffling infinities between the matrix element and the coefficient function. So this immediately raises the question, okay, but if I did so, I mean, either this doesn't make any sense, or there must have been some infinity in my bare Cn, which I did not talk about because I did not talk about how to calculate the coefficient function in next leading order. And when I actually renormalized An, that must have canceled some infinity that was there and I did not talk about. So this immediately raises the question, when I effectively divided Cn by Zn, which infinity was there that I removed? There must have been some infinity in Cn bare, which I removed at the same time as I was removing the infinity from An bare. So this raises the question, is Cn divergent? And the answer is, well, if in order to understand the answer, we have to look at the Feynman diagram. So why did we conclude that An was divergent? Because we looked at the Feynman diagrams and we concluded that we have loop diagrams and the loop diagrams diverge. So what about Cn? Well, we know what Cn is, right? It's the structure function on a quark target. So we have to calculate the structure function on a quark target at next leading order. At leading order, it was just a delta, and see whether we get some divergence. And that divergence must cancel against the divergence of the operator. So let's take a look. So this last chapter is called collinear divergences and factorization. And I guess I'm anticipating what kind of divergence we have. So we want to calculate, I mean, the leading order diagram is still here, right? This is the leading order diagram for DIS on a free quark. What about next leading order? Well, at next leading order, we have two kinds of diagrams. I mean, deep inelastic scattering means there is an incoming virtual photon, an incoming quark. Next leading order are also gluons, but we are not talking about gluons, just to make life easy. So an incoming quark, an incoming virtual photon, and any possible final state. So we have two kinds of corrections. We have either loop corrections, or we have corrections where we have extra stuff in the final state, which are called real emission corrections. So we have either corrections like this, where we have extra stuff in the final state, like an extra gluon, or loop corrections. So these are what is called real or virtual, which are like this. Okay, so when you take, of course, you must take the square modulus of the sum of all these guys, and then when you take the square modulus, these guys have two extra powers of the coupling. So you have the interference between this guy and this guy, 2 powers in the modulus square. This guy has 1 extra power of the coupling, so you take the square modulus, it interferes with itself, and the next order is 2 powers of the coupling. But now you look at all the virtual corrections, and you see that the virtual corrections have the same kinematics as the leading order. So remember, the leading order was proportional to delta of 1 minus x. Okay? These guys, it was proportional to delta of 1 minus x by momentum conservation. You remember, it was just p, q, p plus q. The fact that p plus q squared is equal to 0 gives you delta. But all these guys are the same. So all the virtual corrections have same kinematics as leading order. Sometimes people say virtual has Born kinematics, meaning same kinematics as leading order, which means they are all proportional to delta 1 minus x. Now we are interested in finding some divergence that cancels against a n of mu square, which had this non-trivial n dependence, which means non-trivial x dependence. So these guys are not going to help. They are all proportional to 1. So our only hope is that there is some divergence in these diagrams. And in fact, come to think about it, if we look at these diagrams, we immediately realize that this guy here is a dangerous guy because this guy is actually divergent. So let me show you how. Yeah, I think now I can erase this. So in order to understand the divergence, I want to introduce just a little technology which is not terribly important, but it helps in understanding how this kind of calculation works. And the technology is called Sudakov parametrization of momenta. Okay, let's see whether I got it. I don't have it, doesn't matter. Okay, so I want to look at this diagram by saying I have a gluon emitted here. I have an intermediate momentum p minus k, which is propagating over there. And I want to determine the kinematics of this propagating momentum. And I do this as following. So I write my momentum p like, Sudakov parametrization works in the following way. I write my momenta in terms of light cone basis, which means I introduce a momentum p. I introduce another momentum, so p square is equal to 0, and this is this guy here. I introduce another momentum eta, which has the property that eta square is also equal to 0. However, eta dot p is not equal to 0. So you can think of it in your mind as thinking that p is equal p 0, 0, p, and eta is p 0, 0 minus p, okay? You don't have to write it like this. What I really need is just this. And then I introduce a transverse momentum k perp, where k perp has the property that k perp dot p is equal to k perp dot eta is equal to 0. And you can think of this k perp as being 0, k perp 2 vector 0, right? A basis in this subspace here, okay? So then I can write any momentum in a basis given by p, eta, and k perp. And that's called Sudakov parametrization. Okay, so here I do the following. I write k like 1 minus z times p minus k perp plus y times eta. Okay? Y is fully determined by the condition that k square is equal to 0, right? Because you see k square, so k square is a light-like vector, and k square is equal to, so p square is equal to 0, eta square is equal to 0, so this is 2y 1 minus z p dot eta, which was different from 0 by hypothesis, minus chi perp square, minus because there is the Minkowski metric. So this immediately tells me that y, because k square is equal to 0, this means that y is equal to k perp square divided by, let me write it on the other blackboard. Y is equal to k perp square divided by twice p dot eta 1 minus z. okay? Now, with this, I can calculate P minus K squared, which is the square of the momentum which is propagating here. And what is P minus K equal to using Sudakov parameterization? I can get this immediately here because I see that P minus K is equal to, well, you see, P minus K must compensate. So this was K here. So P minus K must be equal to ZP, because 1 minus ZP plus ZP is equal to incoming P, minus Y eta, because this must add with this, plus K perp. K perp is a 2 vector, okay? And therefore, P minus K square is equal to minus Y Z 2 P dot eta minus K perp square. And if I substitute this Y, which I found here, in here, I immediately get that this is K perp square times 1 minus Z. Okay, because you see this guy simplifies with this guy. I then add up the two terms, and I have Z plus 1 over 1 minus Z. So yeah, this is what I get with a minus sign, I guess. Okay, so you see the point is that P minus K square is proportional to K perp square. Now, what is K perp square? Well, K perp is the transverse momentum of the emitted gluon. Now, I want to calculate the cross-section for that process. Now, the cross-section for that process is d sigma, which is equal d3k over 2k naught, where k naught is actually 1 minus z times p. So this is 1 minus z times p of the modulus square of this guy here, where by modulus square, I mean, you know, the Feynman diagram where I write this guy here. Now, look at this integral here. I mean, this d3k I can write as dz, because the longitudinal component of k is parameterized by e, times d2k perp. And then, you know, I have some factors here. And then from this guy here, I must have a propagator. So there will be 1 over P minus K square times dot, 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 where this is the propagator of the intermediate guy there. And this is proportional to d2K perp divided by K perp square, which is proportional to the log of K perp square. And this integral goes from 0 to infinity because, of course, the transverse momentum of the emitted gluon can be anything. It can be 0. So this guy diverges logarithmically. This is log divergent when K perp goes to 0. And if you look at this diagram, this is the only divergence that is. So the inevitable conclusion is that the singularity that we were looking for that cancels between coefficient function and operator matrix element is the collinear singularity. Collinear, why collinear? The K perp going to 0. K perp going to 0 means that the transverse component of the emitted gluon goes to 0, which means that P minus K is parallel to P. So this is what is called collinear limit, because P minus K is proportional to P, because K perp goes to 0. They are both aligned, okay? And in this collinear limit, I have a collinear singularity, and the collinear singularity is the thing that cancels between coefficient function and operator matrix elements. So this is really, yeah. If I consider the quark to be massive, no, I would have no divergence. So indeed, for this kind of argument, it's crucial that the quark is massless. So you can ask what happens if the quark is massive. So what happens if the quark is massive is that then I have to, okay. Yeah, that's a very good question, actually. So let me go back to my line of argument. So my line of argument was that there is a ultraviolet divergence that was present in the operator matrix element that cancels against the collinear divergence in the coefficient function. So when I look at the diagram here, what I'm really saying here is that I have some operator matrix element here, and the operator matrix element is defined as some matrix element in some initial state. Okay? When I computed the operator matrix element, I assumed that I was having a massless quark, and then I renormalized that massless quark. However, I could have assumed that my operator matrix element was defined in a massive quark state. Okay? In that case, what I would find is that my ultraviolet divergence actually has a natural renormalization scale, which is the mass of the quark at which I'm renormalizing. So, at that point, I would say, what is the scale at which my quark matrix elements are equal to 1? The mass of the quark itself. And then what I would find is that this operator matrix element then depends on a ratio of some ultraviolet scale divided by the mass of the quark itself. Now, the ultraviolet divergence of the operator matrix element matches against the low momentum divergence of this gluon emission here. And then when I combine the two, I get that I have one single scale dependence, which is the ratio of the top scale, which is q squared, divided by the lower scale, which is in the operator matrix element. So what I'm doing here is I'm assuming that I'm having an ultraviolet divergence of the operator matrix element, which is normalized with respect to some arbitrary renormalization scale, which is like the dimensional regularization scale. And then I have an upper scale, which is also defined by some lower arbitrary scale, and I match these two arbitrary scales. If the quark was massive, I wouldn't have to introduce an arbitrary scale. I would have a natural scale, which is the quark mass scale, which is the one where all the divergences disappear. Then I'm simply deciding that all the scale dependence from the quark mass up to some scale is included in the operator matrix element, and from then on is included into coefficient function. So that's a big difference between massive quark and massless quark. Now, this is an important observation because in actual fact, what we are going to do in the end is use this for proton deep inelastic scattering. And of course, the proton does have some natural scale, which will be some strong interaction scale, which is the scale of the bound state. So, if we were computing this diagram in a proton target, we would not get a collinear divergence because the divergence would be cut off by some proton scale, except that we don't know what the proton scale is. And therefore, the reason why the whole argument here is useful is that it allows us to formulate things in such a way that does not depend on what the proton scale is, because at the end of the day, the dependence is only on the upper scale at which we evaluate the PDF, and the lower dependence, in other words, you can think of it in this way. If we could calculate the PDF from first principle, then the dependence on the PDF would not be on the scale at which we evaluate the PDF, the q square, which I had before, divided by some reference scale, but would be the scale at which I evaluate the PDF divided by the proton mass or the natural proton scale that we don't know. Okay? In the case of a massive quark, we can actually do the calculation explicitly, and then we can work out explicitly the dependence of this diagram on the ratio of the scale of the PDF divided by the scale of the quark. And in fact, I'm going to give you a reference in which this calculation is done explicitly. It was actually done by Tommaso, who's sitting in the back, who will be doing the tutorial in the afternoon. So, very good question. More questions? See. Yes, that's absolutely correct. And in fact, Yeah, I wanted to discuss this, but I'm not sure. So if I discuss this, I will not be able to discuss the qualitative properties of PDFs. So take your pick. Yeah. So let me say one more thing, which is important, and then I can at least say one brief word about the. Yeah. So let me just, yeah. Okay, so fine. So, I promised I had a title here, which is collinear divergences and factorization. So you may ask, what does this have to do with factorization? So what this has to do with factorization is the following observation. So and now we've come to the conclusion that this collinear divergence cancels against the ultraviolet divergence of the operator, which then means, however, that the scale dependence of the coefficient function that I calculate by calculating the collinear divergence here, and the scale dependence which I calculate by calculating the operator anomalous dimension must be the same, because remember, the two scale dependencies were compensating. Okay? Now, what's the scale dependence induced by the collinear divergence? This is the really important observation. The scale dependence, which is induced by the collinear divergence, is universal, and it is something which does not depend on the particular process that I'm considering, so deep inelastic scattering. By this, I mean the following. I mean that if I compute the cross-section for this process, I discover that up to corrections expressed by powers of q square, this is equal to the cross-section for this process here with the incoming momentum p minus k in the collinear limit. So p minus k in the collinear limit, p minus k collinear is just z times p. Remember, p minus k was zp minus y eta plus k perp. If k perp goes to 0, this goes to 0. Y was also proportional to k perp. So in collinear limit, this is just z times p. Okay? So this modulo square times the log of q square divided by some renormalization mu square scale, which is now a collinear scale, which will have to match against the ultraviolet scale of the operator when I renormalize, times the cross-section for this. So I'm splitting this line here, times the cross-section for this process here, modulo square. So what I'm saying is that in the collinear limit, and this is true up to corrections that are of order 1 over q square. So power suppressed corrections. Say mu square over q square. Okay. So up to power suppressed corrections, a process in which I have a collinear divergence can always be factored as the cross-section of the process without the collinear divergence, but with the incoming momentum replaced by z times p. Why z times p? Because the incoming emission has actually reduced. So this was p, this was 1 minus zp, and this was z times p, which is entering this guy here. Then I have the integral here, which produces the log, which is the log which I have here. And this factor here is actually, so this is like, so I'm saying that the cross-section for this process is like the cross-section for a process, let me call it sigma naught, the process without the emission, but with Zp, convoluted with some quantity, which I call a splitting function, which in this case I call a PQQ splitting function, which is the cross-section of the process with an incoming quark with momentum p, an outgoing quark with momentum zp, which depends on z, and is convoluted with this guy, times a log of q square. Okay? And what this is telling me is that actually, d sigma d log q square, I'm taking the derivative, is like the splitting function pqq convoluted with sigma, which means that if I take a Mellin transform of both sides, this is like saying that d by d log q square of my coefficient function Cn is equal to gamma n times Cn, provided only gamma n is the Mellin transform of the splitting function pqq here. Okay? And I'm calling it pqq because I only have quarks around. When I also have gluons, things become more complicated. So what I discovered is that this compensation of singularities between the hard matrix element and the parton distribution is a reflection of the fact that whenever I have collinear singularities, the cross-section with an incoming collinear singularity in an incoming parton is factorized in the cross-section without that collinear singularity times a universal factor times a log, okay? And then you understand that this kind of mathematical accident that the structure function was the convolution of, so you remember we had this relation that said that the structure function f of x is a convolution of a structure function with an incoming quark times a parton distribution, is just a reflection of the deeper fact. So that looked like a mathematical accident, that I was rescaling the incoming momentum by x. But now I understand that the rescaling of the incoming momentum by x is just a reflection of the fact that I'm factorizing everything that produces the collinear singularities up to power suppressed corrections in the initial parton distribution. So what was originally something that gave me a prescription to calculate the q-square dependence of the parton distribution is now telling me that any process like this will factor whenever I have collinear singularities in incoming legs with a universal factor, which is the splitting function, which is something whose Mellin transform is the anomalous dimension of the operators, and therefore does not depend on the particular process that I'm looking at. It just depends on the kind of quark that I'm looking at. Okay, so what I constructed for you is essentially a proof of factorization, which I can then use by taking for sigma here, not necessarily deep inelastic scattering, but any process, right? So I can look at any process here where I have an incoming quark, and then I say, well, if I have singularities, collinear singularities in this incoming quark, I can factor this up to power suppressed corrections, where the power suppressed corrections will be suppressed by powers of the hard scale of this process here, and the incoming leg will depend on scale in a universal way, which is dictated by this. Okay, and if I actually solve the renormalization group equation like I did before, and I look at the corresponding equation in X space, so I take an inverse Mellin transform, then I realize that what I'm actually doing is I'm summing, I suppose I can write it here. So when I write my q of q square like I did before, like exponential of an integral d lambda square over lambda square from mu square to q square of gamma n of alpha of lambda square times q of mu square, this was the solution to this equation reshuffled in terms of parton distribution. What I'm actually doing is I'm looking at this process here, I'm iterating the emissions like this, and then I'm saying, okay, I set a scale here, I call this scale, let's say mu square, and then everything which is below I put into my q of mu square, and everything which is above I will put in my q of q square, and I'm just summing repeated emissions. So if I just take the inverse Mellin transform of this, I just get that this is the sort of process that I'm looking at. And since I only have 15 or maybe less minutes left, I guess there are many more things that I could say, but I would probably stop here. And since Alessandro asked the question, let me just make a little comment. So Alessandro asked what about the soft limit? So soft limit means that not only here I have k perp going to 0, but I also have z going to 1. If z goes to 1, you see k. So k perp going to 0 means k is becoming collinear. K perp going to 0 means p minus k is becoming collinear to p. But then let's say z is going to 1. That means that all the components of the form momentum of p are going to 0, which then means that p minus k is equal to the initial p. So the thing that you are emitting has not only 0 transverse component, it has 0 all components. Okay? Now, in this case, you have an even more powerful factorization, which is called iconal factorization. So if I look at this, and then k is going to 0, then I can say that this guy here is equal to this multiplied times a universal factor, which is actually, so this is p, this is k. So when k goes to 0, this is the process with just a single line multiplied by the momentum p mu divided by p dot k. So, if I have any quark line and the quark line emits a gluon, I can, in the limit in which the gluon or photon, in the limit in which the photon form momentum goes to 0, I can just throw away this guy and replace it by this factor, which is called the iconal factor. And then, so it's even more powerful than the collinear singularity, because in the collinear case, according to whether it's a quark that comes in and what have you in the final state, you get some complicated function of x, while here you just get this overall factor. And then this, of course, has the same kinematics as the process without the emission. So it's what Alessandro was saying, it's a delta function. Okay. But okay, this is, it would be a bit lengthy to discuss. Questions so far? Yes. Okay, so what I'm doing here is I'm decomposing any 4 vector into a basis of 4 basis vectors, okay? So the 4 basis vectors I choose are P, which was a light-like vector, another light-like vector, which has the property of having a non-zero scalar product with respect to P. So if you want to fix your mind, you can think as P00P and P00 minus P, okay? Of course, you don't have to take this along the z-axis, but just to understand what I'm saying. And then, so these are 2 basis vectors, which are like, if you want energy and the third component of momentum, except that I'm trading them for these 2 light-like vectors. And then I have 2 more basis vectors, which I define as the 2 vectors that are orthogonal both to p and to eta. So you can think about them as a 2 basis vector in the transverse space, okay? And then the reason why this is useful is that then I look at the emission of a gluon in this case, but any splitting of one particle into 2 as the one that I emit carrying away a longitudinal fraction of the momentum of the original guy. So this is 1 minus z times p in such a way that what is left here is z times p. A transverse part, which is just what it is, it's just transverse momentum conservation. And then a 4th component, which is just determined by on-shell condition. Right? So you see, here I said k carries away fraction 1 minus z. It carries away a transverse component. And then y is determined by asking that k square is equal to 0. Okay? And then I observe that when k goes to 0, then the intermediate propagator goes on shell, and then the intermediate momentum becomes proportional to the original one. And in that case, my original diagram factorizes, the interference disappears, it factorizes into the product of 2 subdiagrams with a universal factor, which is the one that describes the splitting, a log, and the original process with the incoming momentum replaced by z times the incoming momentum. Why? Because I'm in the collinear limit. So in the collinear limit, p minus k has 0 k perp. It has 0 eta component because the eta component was proportional to y, but y, I think it disappeared. Yeah, I erased it, but y was proportional to k perp square, and therefore I'm left with z times p. Okay, so this is like the magic of the collinear limit, right? So this explains why I have this collinear factorization, because each time I have a collinear emission, the interference disappears and the diagram splits into the diagram without the emission, a universal factor, which is the splitting function, and the log, and all this is true up to power suppressed corrections. And the only thing which can screw up this is if I, for example, if I have a hadronic process with more incoming hadrons and I have exchanges between these two hadrons, then things become difficult. But as long as I have only one incoming hadron, this is a rigorous collinear factorization, okay? And by the way, this is what was discovered by Altarelli and Parisi, who actually started from the diagrams and then realized that there is this kind of universal factorization. So thanks for the question, because this is really the main point. More questions? Yes. That's a very good point. So how do we compute the splitting functions? You have two alternatives which produce exactly the same result. And historically, at next leading order, it was first done with the anomalous dimension and then done with the splitting function. In modern times, the two methods are competitive with each other. So you have two alternatives. I mean, one alternative is to compute the diagrams, which I had on this blackboard before, and I erase, so compute the operator matrix elements and just do the ultraviolet renormalization of the operator matrix elements and keep doing that. You know, you're computing loop corrections to operator matrix element at higher orders, and then you take the derivative. And the other possibility is simply computing deep inelastic scattering. So you compute deep inelastic scattering on a free quark target at higher and higher order, and then you extract the coefficient of the collinear singularity. So historically, what happened was that Gross and Wilczek computed the anomalous dimensions of the operators in the late 70s, and then Curci, Formansky, Petroncio in 1980 computed the next leading order corrections to deep inelastic scattering and actually proved that this Altarelli-Parisi argument, which I've just given to you, works to any perturbative order. And you can find the proof in Collins's book, for example. And then, however, so this was next to leading order, and it remained like this for basically 20 years. In the early 2000s, Moth, Thermajan, and Vogt actually calculated deep inelastic scattering up to so you see, in order to get the leading order coefficient function, I have to calculate deep inelastic scattering to next to leading order, right? Because the leading order deep inelastic scattering is just a delta. So if I want to get the leading order splitting function, I have to calculate DIS at next to leading order on a free quark target. Okay. So if I want to get the next to leading order splitting function or anomalous dimension, I have to calculate DIS at next to leading order. So in order to calculate the next to leading order splitting function or anomalous dimensions, I have to calculate DIS up to next cube leading order, which is high. And this was done by Moth, Thermajan, and Vogt, who actually did it using operator, actually computing deep inelastic scattering. So for free, they actually got the next cube leading order coefficient functions and the next leading order anomalous dimensions. Of course, next cube leading order coefficient functions you cannot do anything about until you know the next cube leading order anomalous dimensions. And for that, in the last maybe 3, 4, 5 years, various groups have been trying to compute them. And what they did until now was instead to switch the operator approach. So calculate the matrix elements of operators up to next cube leading order, and then get the anomalous dimension. So you always have these two possibilities. Either you calculate deep inelastic scattering at some order and you extract a collinear singularity, or you calculate operator matrix elements at one less order. But then, which of the two calculations is more difficult? They are comparable. There are advantages and disadvantages. One obvious advantage, if you do the calculation of deep inelastic scattering, is that you immediately get the splitting function as the coefficient of the collinear singularity. If you do the calculation with the operators, you actually get a tower of results for integer n that you have to analytically continue. So, for example, if you do the calculation by brute force, which is what people did in the last years, they actually got some humongous expressions that you cannot even write down. They are a piece of computer code. There are thousands of lines of computer code that give you the value of the Mellin moment for n equal 2, 4, 6, 8, and 10, for example. And then it's very difficult. I mean, you can numerically interpolate, but you don't have a closed form expression. While, of course, if you do DIS, it will be a very long expression, again, a piece of computer code, but at least it's the expression in X space. So you see how it works. Yeah. Yeah, that's a good question. So where does twist enters? Well, I kept telling you that here you have power suppressed corrections. So if you go at high enough Q square, higher twists always lose because you're power suppressed. But if you go at low enough scale, then the two things become comparable. And the thing is the following. So the thing is non-trivial because what does low enough scale mean? Now, the point is that here I'm always assuming that the scale of the process is Q square. But remember that when I started yesterday, I told you that if I look at the process like this, if I take m square x, where this is the invariant mass of the final state, this is Q square times 1 over minus x over x, where x is x Bjerkane. Okay, so you immediately see that if x goes to 1, then the invariant mass of the final state is going to 0. And then if x is going to 1, now here I was always factoring the longitudinal dependence in x from the scale dependence in Q square. But you see that if x is going to 1, then the physical scale of the invariant mass of your final state is actually not Q square, but really Q square 1 minus x. Now, if you actually compute the coefficient function in perturbation theory, you discover that this fact, namely the fact that the physical scale of the final state is not Q square, but Q square times 1 minus x, actually appears as part of the perturbative calculation. And that's a consequence of the infrared divergence that Alessandro was asking about. So you'll discover that the coefficient function that I'm calculating here will contain actually a log of Q, so the coefficient function contains a log of Q square 1 minus x over x. When I factor my collinear singularities, what happens, let's say this is F2 on a quark. This will contain such a log. And then when I write this as my coefficient function Cn times An, what happens is that I split this log. So I write this as a log 1 minus x over x, which I put in the coefficient function, and the log Q square, which I put in the evolution of the operator matrix element. But you see, this means that when x is going to 1, this coefficient function has a very large perturbative correction. And then my perturbation expansion breaks down because I've chosen the wrong physical scale for my final state, so I can't win. And if I start adding up these corrections, so I say, well, at the next perturbative order, I have log square and so on, I end up with something, so at all orders, I end up with a coefficient function which is something like exponential of log of 1 minus x. And this exponential of log 1 minus x, it's actually minus. It's like a 1 over 1 minus x enhancement or suppression. And in fact, however, this was combined with q square. So I cheated because I'm including these two orders in the coefficient function, but q square I only included to fixed order in the evolution. And if I were actually to do the all order thing, I would discover that I have a higher twist corrections, which is of the form lambda square divided q square divided by 1 over minus x. So you see that even if q square is becoming very large, if x is going to 1, the denominator is small, and then the higher twist corrections is big, even if q square is large. And so the answer to your question, when are higher twist corrections important? Generally, higher twist corrections are important whenever in deep inelastic scattering, whenever the mass of the final state is small enough, and that can happen even at large q square if you're going to threshold limit. More in general, whenever the physical scale of the process you're looking at, let me do this way. Whenever the process you're looking at contains on top of a hard scale also a soft scale. So, there are two situations. One situation is when the scale of the physical process you're looking at is small, and then higher twist corrections are obviously important. But then you can say, I'm only looking at hard processes, no problem. There is a subtlety, which is that in hard processes, you can have more scales. And this, which I've shown to you, is an example. This is deep inelastic scattering. You're looking at large q square, so you have one hard large q square scale. But then when x goes to 1, you also have another scale, which is q square 1 minus x, which is a soft scale. And whenever you have two scales with a large scale ratio, then higher twist corrections can again become important. And this happens in DIS. It can happen in jet production, for example, and in many other contexts. And I'm afraid with this, I'll never get to answering the questions that Alessandro would have liked to hear about, which was something about quarks and gluons and soft corrections and qualitative features of PDFs and how many independent anomalous dimensions we have. But it's maybe better to know a few things well than many things in a confused way. So I think this is possibly what. So first of all, let me ask whether there are more questions.
Yes, can I ask you something?
Yes. Yes.
How does what is it that in the end the calculation?
Yeah. So. Yeah. So what can I calculate and what can I compare to data? So this was, I think, the similar question was asked before by someone else. So let me summarize. This is an important question. What I can calculate is the anomalous dimensions and the hard cross-section. So in deep inelastic scattering, the anomalous dimension and the coefficient function. What is the coefficient function? What is the hard cross-section? It's the cross-section with incoming quarks and gluons. So let's say instead of DIS, I'm doing W production at the LHC. Okay, I'm producing W's for which Carlo Rubbia got the Nobel Prize in 1984. So I'm producing a W gauge boson. I need an up quark coming in and a down bar quark also coming in, okay, which I get from two protons at the LHC or a proton and antiproton at the tevatron when the tevatron existed, okay? So how do I calculate this? I simply calculate the cross-section for a quark and an anti-quark to produce a W, and then I can calculate it at one loop. I can calculate it including extra radiation, and this is what I call a partonic cross-section. Okay, this I can calculate in perturbation theory, and as a matter of fact, this W production has been currently computed up to next cube leading order, meaning up to 4 loops, up to order alpha to the alpha. So leading order would be this diagram that I've drawn here. Next to leading order would be either extra emission of gluons or loop corrections, and you keep going up to next cube leading order. This you can calculate in perturbation theory. Okay. The other thing that you can calculate, and this you can do for a W production, you can do it for top production, you can do for jets. I mean, there's.
You calculate the mass of this part.
No, I calculate the Feynman diagrams with an incoming partons and the final state. So for example, when they discovered the Higgs, what did they compare to? When you look at the Higgs cross-section, you calculate the Feynman diagram where you have two gluons coming in, a top quark loop, and the Higgs. This is something that you can calculate. At leading order, it's been calculated 25 years ago, and next to leading order, it has been calculated by Sally Dawson in, I guess, 1992 or something like that, which means that then you have a correction like this, for example. And these are just Feynman diagrams, okay? You calculate the Feynman diagram for the process, and you get a prediction, okay? Now, in order to get this, a prediction that you can compare to LHC data, you have to use factorization. Use factorization means you take this prediction, which is something that you calculate with Feynman diagrams with incoming quarks and gluons, and you combine it, like here, you combine it with splitting functions and this PDF, the operator matrix element. Now, what do you know of the PDF? You know how it depends on scale, because it depends on scale with these PQQs, which you also calculate from Feynman diagrams, like we were saying when he asked the questions. You calculate them either from operator matrix element or from DIS. So you know how this guy here depends on scale. And then, but then you say, what is the initial condition of this guy, which is the PDF? That I don't know. So what I do in practice, which is what I did not have time to discuss, but you'll see it in the tutorial. What I do in practice is I take a process I know very well. So in the tutorial, Tommaso will take deep inelastic scattering, which we know very well, okay? So in deep inelastic scattering, I have a bunch of data. I can calculate the coefficient function. At leading order, it's just a delta. I can calculate the scale dependence of the PDF, and then I don't know what the PDF is, but I have the data, so I compare the data, and I leave the PDF as an unknown, and I extract it from the data. But then the PDF is a property of the proton. It's not a property of deep inelastic scattering, so that same PDF which I extracted from deep inelastic scattering, I will use to calculate Higgs production at the LHC. I can think of it as the probability of pulling out a quark and a gluon from the proton. So once again, I calculate the partonic process, which is the process with incoming quarks and gluon. I calculate the scale dependence of the PDFs. I extract the PDF by comparing data to my theoretical prediction with the PDF left as unknown in something I know very well, and then I use that PDF to predict another process. And that.
The next question, in all this, you have to assume in the theory, you assume the structure of the particle, let's say, which interact, but not the reaction mechanism. Is the reaction mechanism clear? And then you use only the formalism for the structure, or is there also the
So, you know, as long as you're considering processes for which QCD factorization works, then the reaction mechanism is completely controlled by the theory. I mean, it is given by the Feynman diagrams, okay? And you know, what I tried to explain in these 4 hours is why this happens. And the deep reason why this happens is that in this dominant collinear region, which dominates out, up to power suppressed corrections, the process of pulling out a quark or a gluon from the proton factorizes, meaning that there is no interference with respect to the process with incoming quarks and gluons. And the process with incoming quarks and gluons is completely, I mean, there the reaction mechanism is dictated by the Lagrangian of perturbative QCD and Feynman diagrams. Okay, so to the extent that you can use collinear factorization, then the reaction mechanism is a Feynman diagram calculation, and the input is something where you know the scale dependence and nothing else. So everything else has to be extracted from the data, and this is the whole game of PDF determination, which is what you'll see in the tutorial. And what you'll see in the tutorial is basically taking the simplest case, deep inelastic scattering with only one PDF, only one structure function, and comparing the data, actual real data for the structure function with this factorization formula, and by comparing the two, extracting the PDFs. And then there is a whole set of complications operations that I didn't have time to discuss, but you'll see in the tutorial that have to do with how you treat the uncertainty, because the data will have the uncertainty and the PDF will have an uncertainty. And remember that at the end of the day, you're extracting a function of x, which is a function. So it's an infinite amount of information from some data which are discrete, because however many data you have is just a bunch of data points. So you're doing an inverse problem, which is an ill-posed inverse problem, because you're extracting a function from a finite number of data, so you have to make some assumption in order to get a unique answer. And this is the whole game that will be discussed at this point in the tutorials.